Okay, I'll be back.
What's that? You're now living the dream. You're living the dream?
All right, it's 5:30. Let's go ahead and get started. All right, good evening, everyone. How's everyone doing today?
Pretty good.
Good to hear. All right, so today we're going to be finishing up our lecture notes on truss elements, and so I have basically just one more example and just one more concept left for trusses, and so hopefully we can finish that within the first maybe one half, 2/3 of the class, and then the rest of the time today we'll be starting our next thing. But I also forgot that we have an evacuation drill today. Okay, so we may have to move soon, but until they kick us out, let's continue with the class. So,
What if we just turn off the lights?
well, I'll still be talking, so they'll hear me. So, okay. All right, let's get out of here. All right, Zoom people, we'll be right back. I think we'll be back maybe like 15 minutes. Okay.
Bye.
We got to make sure all the grad students are aware of
clear area 150 feet from all structures. Attention, attention. proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated. All occupants must immediately gather their personal belongings and proceed to the nearest stairway or ground floor exit. Do not use the elevator. Exit the building and move to a clear area 150 feet from all structures. Attention, attention, attention. An emergency has been reported and the building must be evacuated.
All right, no, it's all my iPad. Good. All right, Zoom people, we're back. Sorry, I forgot that there was a drill today. It's funny because I was looking at the notes and kind of thank you. I was looking at the notes in terms of where we were, and I was like, oh, we're like kind of ahead of schedule a little bit. You know, we might be able to start beam stuff, but you know, of course, whenever that happens, the gods will be like, fuck your schedule. So, you know, guess we're back on our regular schedule. So I'm gonna give a second just for everyone to kind of walk back in and kind of get settled, and then we'll get started for today. Okay, all right, so let's get started for today. So a little bit of a delayed start, but we're back. You know, for any people that are watching this on YouTube days after, you know, the reason there was kind of a big delay before the start of lecture was because there was an emergency drill. So, but okay, let's get started. So let's get back into truss equations. All right. So we're at the tail end of this set of lecture notes, and so you know we've been here for quite a while, and so you know the plan for today is kind of just to do one more example, just so you can kind of see the whole thing front to back, and then we're going to cover this idea of symmetry near the end. Okay. Okay, but just to kind of review kind of where we've been. So basically, we're looking at 2D finite element problems that involve trusses that are oriented in an arbitrary fashion. Okay. I keep getting calls from the school, I think, just to let us know that the drill is concluded. But my phone has decided that the school
Spam.
phone number is spam. So I don't know if that's a good thing or a bad thing.
Pixel?
Yeah, Pixel. Yeah. Yeah. So maybe maybe they need to stop calling people. Yeah, it's just spam. Okay. All right. So we were looking at basically problems like this, right? So we had our truss bar. This. Right. So again, so the biggest kind of difference that we've been working on this week and kind of end of last week is that our bars can be oriented in 2 dimensions, right? And so the biggest change that this occurs, that this essentially changes the form of our element stiffness matrix. Okay. Right. So of course, I think the part that everyone kind of feels the most is the fact that our element stiffness matrix quadrupled in size, right? Instead of being a 2x2 element stiffness matrix with only 4 entries you have to compute, now our element stiffness matrix is 4x4 with 16 entries to compute. So that it makes that step, which is already tedious, take 4 times longer. And so and the reason for this is because since now we're in 2D, we have to account for the fact that every node in our finite element geometry can deform in both the X and Y direction. Okay. Good. Okay. So before we jump into another example, we're going to introduce a new type of support, right? So far, in all of our problems, we've only been working with a single type of constraint, okay? So these types of constraints here are what I call kind of pin supports. Okay. So those pin supports are often they're always anchored to the ground, right? And so what that means is that they prevent deformation in both the X and Y direction. Okay. And so we saw that in the example that we did at the end of class on Tuesday, right? So, for every node that's connected to a pin support, right, we basically said both the X deformation and, well, that should be the Y direction, right? So that both the Y deformation and the X deformation equal to 0, okay? And so what that essentially did is that knocked out 2 rows in our matrix. All right, so pins are not the only type of support that we can have, right? In fact, we'll see another type of support when we get into beams. But for now, let's introduce the idea of a roller support. So a roller support, unlike a pin support, will only prevent deformation in one direction. Okay. So roller support will look something like this. Right, so it literally looks like a roller skate at the end of your truss bar. Okay. Okay. So whenever you have a roller support, you have to look and see which direction the rowers are going, right? And so in this direction, the rowers are going, in the X direction. And so what that basically means is that the x direction is free to deform. Okay. Whereas the y direction is going to be constrained. Okay. All right. And so what this means is that, when you go to apply boundary conditions to your global linear system, then the row that corresponds to dy in this case will be replaced with our boundary condition. Okay. Whereas the row for dx, we're going to leave that one alone. Okay. So rollers kind of give a very interesting tool in our toolbox to create some more interesting structures that we can analyze. Okay. Okay. Any questions on roller supports before we jump into another example problem? Okay. All right. So let's go ahead and do another example. Okay. So for this one's going to be a little bit more straightforward. Okay. So we only have two elements here. So let's look at the following structure. Okay. We have basically kind of an overhanging, point at the end, right? Supported by two truss bars. Okay. So you have truss A, truss B. The angle in between these we'll say is 30 degrees. Okay. The length of the top truss bar is going to be 10 feet. The length of the bottom truss bar is going to be 5 feet. Okay. Let's go ahead and label the nodes. And so the node at the end where the two elements converge, we'll call that node 1. The point at the pin support for element A, we'll call that node 2. And then the location where we have the roller support, we'll call that node 3. Okay. Okay. And then we also need to add our load. I'm not going to forget that this time. Okay. We're going to assume that we have a vertical load of 25,000 pounds being applied in the y direction, or should I say negative y direction at node 1. Okay. Okay, let's also specify the properties of the bars, right? So we're going to say both bars have the exact same Young's modulus and both same cross-sectional area. Okay. So we'll say E here is 30 times 10 to the 6 psi. And the cross-sectional area will be 1 inch square. Okay. All right, so given this problem here, let's go ahead and write out what we're going to look for. Okay. So let's solve. All right, so first thing we're going to solve for is the displacement of all the nodes in the system. Right. And then two, let's also solve for the stresses in each of the two elements here, in element A and element B. Okay. So if you remember right at the end of class on Tuesday, we went over the equations that we can use to compute stress in these elements. Okay. Okay. All right. So that's the problem. So we're going to be working on that, probably at least for the next half hour. Okay. Any questions just on the setup for the problem? Okay. All right. So let's go ahead and get started. So just like any other finite element problem, we're going to start with the element stiffness matrices. Okay. All right. So we're going to go element by element. Okay. So let's start with element A. So remember, when we're writing out these element stiffness matrices for these 2D truss elements, we need to find out, or first we need to kind of specify what the angle for this element is. Okay. Okay. All right. So remember the rules that we use to determine angle, right? So remember, to determine angle, you're going to find the lower numbered node, and you're going to draw the positive x-axis on that node. Okay. So let me draw element A here. Okay. So element A looks something like this. Right? We know that it's making an angle of 30 degrees with the horizontal, okay? And so element A is oriented such that node 1 is on the bottom and node 2 is up top, okay? All right, so if we draw an origin system from the lower numbered node, so let's say that we, take that node 1 and we draw a positive x-axis, right? And so what we're going to do from here is we're going to rotate counterclockwise until we are in the orientation of the element, okay? So let's start from the positive x-axis and then let's rotate counterclockwise until we reach that point there, okay? So that amount of rotation that we're doing, that is going to be our angle theta, okay? So I think this is probably the first, I would say, weird one that we've gone over, because I think the example that we did on Tuesday, the angles were more or less pretty straightforward. But this is the first time where we're doing an angle that's beyond 90 degrees, okay? So you can see from this figure here, you can kind of, it's, maybe not fully straightforward, but we can kind of see that the rotation angle here is going to be 150 degrees. And the way I determine that is that, I know that if you were to take the x-axis and rotate it completely over, like a full half turn, that would be 180. But since we're not going all the way over, we're stopping 30 degrees short. That means our rotation angle has to be 150 degrees. Okay. Okay. All right. So unfortunately, with 150 degrees, it does make the computations a little bit annoying, just because we're not doing just zeros and ones or √2/2. Okay. So let's go ahead and compute cosine and sine. All right. So first we have cosine. So C is cosine of 150 degrees. Okay. This is going to be a negative √3/2. Okay. And then S, we have sine of 150 degrees. This is going to be a positive 1/2. Okay. So this would be kind of the first time we kind of just have to kind of just, pull up our big boy pants and just kind of do a bunch of these sine and cosine calculations. Okay. Okay. So let's go ahead and write out the element stiffness matrix. So element stiffness matrix, we have AE over L multiplied by. Okay. All right. So first row we have is we have cosine squared. Okay. We have cosine sine. We have minus cosine squared. And then we have minus cosine sine. Okay. Okay, so let's go ahead and plug in. So cosine squared is, cosine is minus √3/2. So we square that, and that gives us a positive 3/4. Okay. Then next we have cosine times sine. So cosine times sine is a minus root 3 over 2 multiplied by 1/2. And so that's going to give us a minus root 3 over 4. Okay. All right, next we have a minus cosine squared. So cosine squared, we already know from the first entry is 3/4. We add a minus sign. That's going to give us a minus 3/4. And then we have minus cosine sine, and so that's going to be a opposite sign of what we had in the second entry. So that is a positive root 3 over 4. Okay, so like we usually do, we're going to take advantage of the symmetry of our element stiffness matrix. And so we're just going to write all the entries in that first row down into the first column of our matrix. Okay, so first we have a minus root 3 over 4 in the second row, first column. Next, we have a minus 3/4 in the third row, first column. And then in the fourth row, first column, we have a positive root 3 over 4. Okay, I'm going to clean this up a little bit just so that it's more legible. But I just hopefully everyone kind of has the equations down for this. Okay, so this is going to be a positive 3/4. Minus root 3 over 4. This is minus 3/4. And then we have the root 3 over 4. Okay. All right. So one interesting observation that maybe some of you have noticed, and I've had conversations with some of you about this as well, right? You'll notice that the way that we formulate these element stiffness matrices, the entry that's on the main diagonal of the element stiffness matrix is always going to be positive, okay? And there's a very, very good reason for that, because we could have easily defined this element stiffness matrix so that it's not positive. We can kind of do it in a more haphazard way. But the reason we always have a positive entry on the main diagonal is that it actually improves the numerics of our solution, okay? So, like we've seen in our previous finite element problems, eventually we're going to reach a point where we have this gigantic linear system, a bunch of equations, a bunch of unknowns, right? And so typically when you take that system, you pass it to a computer, the computer is going to use a very specific, well, it's not very specific, but a class of solution methods to solve it called iterative linear solutions, okay? And the thing with those algorithms that, they perform a lot better if you have a positive semi-definite matrix, okay? And the way to kind of get that is, or one easy way to achieve that is to make sure that your main diagonal is positive, okay? So that's always one good thing to check your calculations, because, I know with these, 2D truss elements with, all these sines and cosines, you have negatives kind of flying everywhere. So, one good thing to check is to always check and make sure that your main diagonal is positive numbers. So that's a good sanity check. Because if it's not, if you have a negative on the main diagonal, you might have misplaced something at some point, in your calculations. Okay. Okay. All right. So let's go to the next row. So the next row, we have a sine squared. Then next to that, we have a minus cosine sine, and then a minus sine squared. Okay, so let's go ahead and plug in for this. So sine of the angle is 150. Okay. All right, question from the chat. So question says, for a test, will you provide a key for the matrix, or do we need to memorize all placements of all the sine cosine functions? So for the exams, I let you guys bring an 8.5 by 11 cheat sheet. You can write on both sides, so you can write whatever you want on them. So I think people just because these matrices are kind of hard to memorize, and so I think most people will write the equations for those on there. Yeah. Okay. All right. So let's go ahead and fill in the values for this. And so sine squared. So sine is 1/2. So we have a positive 1/4. Minus cosine sine. We've already computed that. That is a positive root 3 over 4. And then minus sine squared. That's going to be a minus 1/4. Okay. All right, and then just like we did previously, let's go ahead and write these entries into the column. So we have a positive root 3 over 4 and then a minus 1/4. Okay. Okay, so let me go ahead and just clean this up just so that we can kind of read it a bit more easily. Positive 1/4, positive root 3 over 4, minus 1/4. Okay. Okay. Third row, we have cosine squared on the main diagonal, and then on the off diagonal, we have cosine sine. Okay. All right, we've computed both of these already. So cosine squared we know is 3/4 positive, and cosine sine is a minus root 3 over 4. Okay, so we'll take that minus root 3 over 4. We'll go ahead and write that down into the bottom. Okay. All right. Then we'll just kind of clean this up. All right, 3/4 minus root 3 over 4. And then in the bottom right-hand corner, we have just sine squared, and sine squared we know is 1/4. Okay. All right. So it is a little bit more annoying when you're working with, kind of factors of 30 degrees, 60 degrees, just because, the entries get a bit more, a little bit more non-homogeneous. But this is kind of as crazy as I'll make you guys do. So I won't give you guys anything weird, any weird angles like 72 degrees or something like that. So and so if you remember kind of your cosine sines for 45, 135, the nice ones, then you should be good for these ones. Okay. All right, and then last thing we'll do is we'll make a note of the nodes that element A is attached to. Okay. All right, so element A is attached to nodes 1 and 2, and so we're going to write those into our matrix. So d1x, d1y, d2x, d2y. Okay. Okay. Oh, let's write in the coefficient out in front, right? So if we have all those entries, okay. Only thing to note is that the length was given to us in terms of feet, but in order to be compatible with the different with the other entries there, you have to convert that feet to inches, right? So 10 feet is the same as 120 inches. Okay, and so if we plug that in, we plug that into AE over L, and what we get from that is 2.5 times 10 to the 5th pound per inch. All right, any questions on that element stiffness matrix there? Okay. All right, so that's element A, right? So thankfully that's the one that's a bit more annoying to compute. Okay. All right, so next one we'll do is element B. Okay. All right, so let me go ahead and draw element B here. So element B looks like the following. So we have node 1 on the right, node 3 on the left. Okay. Right, so remember, first thing we need to determine is the angle, right? And so if we do the same thing, so let's go ahead and draw the origin at the lower number node, which is node 1. We'll make that go in the positive x direction. Okay. So in order to get the element, in order to get this into the same orientation as the element, we actually have to rotate 180 degrees. Okay. So theta in this case, my mouth said theta, but my pen said phi. Right. In order to get theta in this case, is going to be 180 degrees. Okay. So 180 is actually very nice because we know that cosine of 180, right? Cosine of 180 is -1, and then sine of 180 is 0. Okay. So 0 is fantastic. And so that means that any term with or any entry in the element stiffness matrix with sign, we're just going to zero it out and set it equal to 0. Okay. So for this one, I'm just going to write it out, but you can kind of verify the calculations and kind of do them yourself. Okay. But for angles that are 0, 90, 180, 270, the element stiffness matrix is pretty easy because you're going to end up with a lot of zeros. Okay. All right. So for element B, our element stiffness matrix looks like the following. So we have 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, and then 0, 0, 0, 0. And then we make note of the nodes that element B is connected to. So we have D1x, D1y, D3x, D3y. Okay. Okay. And then let's go ahead and compute the entry out in front. And so we have AE over L for element B. So the Young's modulus and the cross-sectional area for element B are the same as element A. The only difference is that it has half the length. Okay. And so that means our coefficient in front is 5 times 10 to the 5th pound per inch. Okay, good. All right, so now that we have our element stiffness matrices, we are ready to assemble them together into our global linear system, right? So let's go ahead and do that. So we have assembly. Okay, so thankfully for this one, it's not going to be as crazy as the previous one because we only have 3 nodes. And so our global linear system in this case will have 6 rows and 6 columns. Okay. All right. Okay, so our 6 rows are D1x, D1y, D2x, D2y, D3x, D3y. And then just like before, we'll write the same things into the columns. So D1x, D1y, D2x, D2y, D3x, D3y. Okay. All right, so we only have two elements to add here. So let's start with element A. Okay. Element A is connected to nodes 1 and 2. So let's go ahead and box off that part of the global linear system. Okay. So nodes 1 and 2 are right next to each other, so we can just kind of do one just big contiguous block, just like that. Okay. Now, of course, the entries in this are going to be very annoying because we don't have nice 1/2s, and in fact, we have √3s of all things. Okay. Right, so we're not going to compute every individual one, at least not by hand here, but I am going to write the end. And so, this is going to be another thing where, you can go ahead and verify these values. Okay. One thing I will do for sure is that, since we have everything multiplied by 10 to the 5th, I'm just going to factor that out, and that'll just be a coefficient out in front. Okay. All right. So, so the entries in this matrix, and so it's going to get a bit messy, but I'm going to go ahead and write them in anyway. So we have 6.875 minus 1.08 minus 1.875, 1.08. Okay. Next row we have minus 1.08, 0.625, 1.08, 0.625, minus 0.625, excuse me. Okay. Then we have a minus 1.875, 1.08, 1.875, minus 1.08. Okay. And we have positive 1.08 minus 0.625 minus 1.08 and 0.625. Okay. Yeah, it's a lot of numbers. But remember the way that we got these numbers is that we basically did the multiplication. So if you look back at the element stiffness matrix for element A, we had basically 2.5 times 10 to the fifth, and we're multiplying that by all of the the entries within the matrix, which are combinations of sines and cosine of 150 degrees. And so that's why we end up with kind of a lot of weird numbers. But as I was speaking, I actually did notice one typo. So actually the top left entry, eventually it's going to become 6.875 because we're going to add the contribution from the other element. But actually just from element A, it's not 6.875, it's actually 1.875. So yeah, that was my mistake. So in the top left entry, just kind of correct that in your notes. It should be 1.875, not 6.875. It does turn to 6.875 eventually, but that's after we add the contribution from element B. Okay. Oh, just highlighted actually. Okay, question, yes.
On exams, are we gonna have to compute answers and with that said, our calculators allowed?
So I do expect you guys to compute the entries in a matrix like this. Mm-hmm. And so yes, calculators are allowed, but they're not going to be like this. They're going to be much simpler. So I'm not going to give you, usually I do the worst angle to use like 45 degrees.
Oh.
Yeah, because the 45-degree matrix is much easier because it's all 1/2 space.
Right.
Yeah. Okay. Mm-hmm. Yeah, you're not going to be responsible for finding the final solution in terms of the nodal displacements, but you do need to set up the matrix. Okay, all right, so that's our element stiffness matrix for element A. Let's do the same thing for element B. Okay. Thankfully, element B is a lot more straightforward. Okay, so element B, this is nodes 1 and 3. All right, so let's go ahead and box out the different areas for element B. Okay, so we have that entry right. We have that 2x2 box up there. That's for node 1, node 1. Then we have that area right there. So that's nodes 1 and 3. We have this entry here. That was a terrible box. And then we have this area right here. Okay. All right, so let's go ahead and put in the entries for this, for this element stiffness matrix here. Okay. So we'll start in the top left with the D1 X D1Y, D1 X D1Y. Okay. So we're going to add a +5 in the top left. Then we're going to add zeros on everywhere else. Okay. In the top right area, we have a -5, 0, 0, 0. Okay. In the bottom left, we have -5, 0, 0, 0. And then in the bottom right, we have 5, 0, 0, 0. Okay. Okay. And then of course, everywhere that's not boxed, that's not part of an element, we're just going to fill that in with zeros. Okay. Okay. And so the only place where we have to provide some addition is going to be in the very top left entry. So remember, that was the typo that I made before. So if you take 1.875, you add 5 to it, you end up with 6.875. Okay. But I'll leave it like this just because I think it's a bit clearer, in terms of where all the entries come from. All right. Any questions on this step here? All right. So now that our assembly step is done, the next step is to apply our boundary conditions. Okay, so this is where things get new. Okay. Okay, so just like we did with the previous example, let's just write out what the boundary conditions are, and then we'll just directly apply them to the matrix above. Okay. All right, so we have two supports here. So we have two constraints, right? So in node two, okay, node two, we have our pin support, right? And so we know from earlier that pin supports basically will eliminate both components of the deformation. And so this is basically going to say that d2x is equal to d2y is equal to 0. Okay. So that means we're going to make modifications to both the d2x and d2y rows. Okay. Okay, so let's start with that actually. Okay. Oh, and we need our forcing vector here. So I'm going to set that's equal to f1x, f1y, f2x, f2y, f3x, f3y. Okay. All right, so if d2x and d2y are going to be equal to 0, so that means we're going to take the third row, and that which corresponds to d2x, and the fourth row, which corresponds to d2y, and we're going to basically eliminate those from our system. Okay. Okay, so let me go ahead and let's use yellow. Okay. Okay, so let's start with the third row. So we have this row right here. Okay. So remember, when we have a support or a Dirichlet boundary condition, we're going to eliminate the entire row. So we're going to take everything and turn it into zeros. Okay. With the exception of the main diagonal. So on the main diagonal, we're going to put a 1. Okay. So for the third row, the location for the 1 is going to be on the third column. Okay. So we're going to have 0, 0, 1, 0, 0, 0. Okay. And then on the right-hand side in the forcing vector, we're going to have a 0 there as well. Okay, and then same thing for the fourth row, right? So fourth row, we also have that's part of node 2. Okay. And since we have a pin support at node 2, that means that row is also going to be replaced in our matrix. Okay. All right, so let's go ahead and erase all the entries in row 4. And let's write in the entries here. Okay. So for the fourth row, that means the fourth entry of that row is going to be a 1. So that's 0, 0, 0, 1, 0, 0. And then on the right-hand side, we have 0. Okay. All right, question in the chat. So can I explain briefly why the 1 is in the third column for the third row? Yeah, for sure. So remember, the kind of the purpose of these of modifying these rows is we're basically replacing those equations by our Dirichlet boundary condition, right? And so we come back down here, our Dirichlet boundary condition states that at node 2, the pin support is going to force both the deformation components equal to 0, right? And so essentially, we're going to have two equations here. So we have d2x is equal to 0, and d2y is equal to 0, okay? So essentially what we're doing by replacing the rows in the matrix, we're taking the row that was there previously, and that row that was there previously represented, remember, each row in our system here represents a linear equation, right? So we're basically taking that row and we're replacing it with our boundary condition equation instead, okay? So we're basically saying that, whatever was there before, we're replacing it with the equation d2x is equal to 0, right? So the reason we have the 1 in the third column there is that, remember, the way that we obtain our linear equation is we take our row, okay? You can, for all intents and purposes, you can consider it as a row vector, and then you're multiplying it by this column vector of unknown quantities here, right? And so you're basically taking the dot product between these two vectors. And so if you do that, we get 0 times d1x plus 0 times d1y plus, we have our 1 1 times d2x plus 0 times d2y plus 0 times d3x plus 0 times d3y, and all that's equal to 0. Okay, so the reason we put the 1 in the third entry is just to make sure that, you know, that entry in that equation is activated to match with this equation. Does that make sense why we do that? Okay, good. Okay, all right. So that is our boundary condition for node 2. Okay, so let's do the same thing for node 3. So node 3 also has a support. Okay. So node 3, this is the new one. So this is the support we haven't seen yet. So this is the roller support. So remember, the roller support is only going to eliminate one component of the deformation, and that is the component that's kind of perpendicular to the wall. Okay. So if we go back to our diagram for the problem, okay, we can see that our roller support is this guy right here. Okay. So since the wheels are kind of facing up vertically on the wall, that means that this roller support is going to prevent deformations in the x direction. Okay. So basically, we're going to say that d3x is equal to 0, okay, while d3y is free. Okay. So because the wheels are kind of in that vertical direction, there's nothing limiting the deformation in that direction. Okay. All right. So mathematically, what that means is that, you know, we're going to set d3x is equal to 0. So we're going to do the exact same thing we did for node 2, where, you know, we're going to replace that d3x row, which in this case is the 5th row in the matrix. Okay. But the last row in the matrix, d3y, okay, since d3y is free, that means we're not going to touch that row in the matrix at all. We're just going to leave it as it is. Okay, so let's go ahead and do that. Okay. So the d3x row is this row right here. Okay. So I'm going to do the same thing. I'm just going to replace everything with zeros except for the diagonal entry. Okay. Oops. Oh, that's fine. So good thing is that most of these were 0. So I just erased a 0, just put another 0 there. Okay. And then right-hand side, we're going to have 0 for that. Okay. But then the 6th row in the matrix, which corresponds to d3y, we're just going to leave it alone. It's not going to, it's, you know, it's not constrained by our boundary condition. Okay. Okay. So after applying those Dirichlet boundary conditions, we are left with the following matrix. Okay. Last thing that we need to do is we need to apply our load. Okay. And so if you go back to the diagram, we only had one load that's being applied on our geometry, which is a load in the negative y direction on node 1. Okay, so that means F1y, so used to writing D's, F1y is equal to minus 25,000 pounds. Okay. We'll also take this opportunity, you know, for every other node that we haven't touched yet with the boundary condition, we'll go ahead and set the right-hand side of that equal to 0 as well. Okay. And so those other nodes that we have here, there's only 2. So we're going to set f1x is equal to 0, and then f3y also equal to 0. Okay. Okay. So let's go ahead and make those changes. And so those are pretty straightforward. Okay. Okay. So we have f1y. Let's start with that one. That's our non-zero one. So f1y, the second entry in our forcing vector, that's going to be a minus 25,000 pounds. And then F1x, F3y, both of those are going to be 0. Okay. All right, good. All right, and so we arrived at the end of another finite element problem. And again, it only took us 30 minutes because I have, narrating every single step kind of takes a while. But any questions on this problem here? Okay, good. So, once you reach this point, you can just take this matrix and just throw it into MATLAB and solve. But if you actually do that for this problem, you'll actually receive an error in the solution, right? And why is that? So let me just kind of clear some space here, just to kind of make things a bit more clear. And let me kind of bring your attention to the last row in the matrix, okay? And the last column of the matrix as well, okay? All right, so what do you notice about those things that I've highlighted? They're all zeros, right? And so that means that, so this actually means quite a few things. But if you get a situation where you're doing a finite element problem and you end up with an entire row of zeros, an entire column of zeros, and oftentimes, those two should match up exactly. So that it should be the same number row and same number column, right? So this is a very special phenomenon that basically says that your system is under constraint. Okay? So that basically means that, if you were to kind of, have this structure the way it is and apply a force, it's not going to be able to hold that configuration. Okay. Right. So another way to say that is the geometry is unstable. Right. And so if we actually go back to the problem geometry, now that with this knowledge here, it actually kind of becomes pretty obvious, right? So let's go back to the problem geometry. Okay. Okay. So with this problem geometry here, right, and knowing the fact that, truss elements, at least for under our assumptions, are only able to expand and contract, right? It doesn't make sense for this geometry to actually be stable, right? Because what's going to happen? So let's say that you have a structure, you put it like this, you put a pin support at the top, that's fine. But then for the bottom support, you put a roller, okay? Even without applying any force, right? And so, by knowing the fact that these truss bars are going to have some weight, right? What we expect to happen is that this is actually going to start sliding down because there's nothing actually here that's actually securing that roller in place, right? So, normally, if you did want to secure it, maybe you can apply a force in this direction to kind of smush that roller against the wall to kind of have friction help you kind of hold that in place. But we don't have that here, right? So we only have vertical forces. And so what we expect is that this roller is not going to stay in that position. It's going to roll downwards, okay? And that reality is actually reflected in our finite element solution as well. The fact that we have zeros in that entire row and in that entire column, okay? So if you run into a situation like this, one thing you can say is that, this problem is unsolvable. This geometry is not stable at all, okay? And that's perfectly valid. But if you did want to solve it, you would have to alter the constraints of the problem, okay? Okay. Now, of course, you wouldn't be able to do this in reality. So, let's say that you have like a CAD model or a structure that, you're analyzing as part of a company. If you get something that's under constraint, you don't just make something up in a computer just to get results, right? You have to tell your company and the design engineer that, hey, this is not going to work. This building is going to fall apart, right? But if you did want to make it solvable, this is how you would do it, right? And so one way we can make this solvable is that we can transform that roller support, and let's say we change it to a pin support, okay? Right? And so as a pin support, that's going to eliminate any kind of deformation in the y direction, okay? And then numerically, what that's going to do, just like we did for all the other Dirichlet boundary conditions, it's going to put a 1 in that main diagonal slot right there, right? So on the six row, 6 column slot, right? That right there, very simple fix kind of fixes our entire problem. And then now we can kind of solve the solution, okay? But remember, this is kind of something that we kind of just made up, okay? But this information is helpful too, because now you can kind of take these results and kind of tell the design engineer that, hey, this support here, it's under constrained. We need to improve it. We need to make it more sturdy, add a fixed support, pin support in order to make it stable, okay? All right, question. So on a homework or test, do we do that, or do we leave it as unsolvable? So if you do get this on a homework or test, you can just say that it's unsolvable, because I'm probably giving you that problem on purpose just to see if you would notice it. But for the most part, I'm going to try not to give it to you unless it's something where I want you guys to notice it. Yeah. Mm-hmm. All right, so this issue here, of having a under constrained system, this becomes less of an issue once we start talking about beams and frames, but it does become an issue. Yeah, spoilers. There is a problem like this on homework 1, so it is something that I did want you guys to notice, but in general, I don't try to trick you. That's the main thing. So yeah, if I do give you a problem on it, it's something I want you to notice and make note of. Yeah. All right. Any questions on this? Okay. All right. So last thing that we'll go over today, just in the last 5 minutes, is we're going to just very quickly talk about the concept of symmetry in finite element geometries. Okay. Okay. So symmetry is very fascinating, and it's kind of the way that FEA engineers kind of show off to each other. Basically that people say that, oh, I have this really tough problem. Oh, but I use symmetry and I cut it this way, and now it's way simpler, right? So symmetry, if you get good at it, it helps your problem tremendously. Okay. So symmetry is basically any part of your geometry or your loading or your boundary conditions that can be basically exactly the same on one part than the other. Okay. 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 And so when I say exactly the same, it's not just the geometry. And so that also means that the loading and the boundary conditions are also the same as well. Okay. So for example, let's look at this geometry here. Okay. All right, so let's say that we have an assembly of truss elements that look like this, right? So we have 4 truss bars, right? And let's say that we're applying a load down the middle here, okay? And so if we look at the left-hand side of this structure and the right-hand side of the structure, they are exactly the same, right? And so when you have symmetry, basically what you can say is that, I don't have to solve this exact same problem, right? I can solve, in this case, I can just solve half of the problem. And then I can just make the assumption that the other half is doing the exact same thing. Okay. All right. So in these situations, you can basically just take you can take a pizza cutter, just cut right down the middle. Okay. And only solve maybe this side of the system. Okay. And then you're just basically going to assume that the exact same thing is going to happen on the other side. Okay. Okay. Right. So symmetry is fantastic. And it's something that's kind of really hard to teach because it's something you kind of just have to start looking at patterns and seeing them. But you have to be very careful because I think people get a little bit too symmetry happy. Okay. So remember, in order to actually apply a symmetry cut, not only the geometry, but the boundary conditions have to be the same as well. Okay. So that symmetry cut worked when our load was just completely vertically down. Okay. But let's say instead that we apply our load in kind of an oblique direction like that. Okay. So it's no longer kind of symmetrical, but it's kind of biased to one side versus the other. Okay. And so in this case, where the loading is not symmetrical, this prevents you from using symmetry in a problem like this. Okay. So kind of the rule of thumb that I use with symmetry. So if you are going to use it in your problem, you should think about, based on what I can observe from the problem here, do I expect any deformation or any displacement to occur into or out of the symmetry plane? Bless you. Okay. And so if the answer is no, then yeah, then you can apply symmetry. But if there's some aspect of the solution where you do expect some deformation into or out of the symmetry plane, then you probably can't apply symmetry there. Okay. All right. Any final questions on this before we wrap it up for the week? Okay. All right. So thank you guys for coming today. You should have everything that you need to do homework 1 now. Even kind of the unsolvable under constrained ones. Let me kind of clarify my comments on that a bit more. So, if you have an under constrained structure, most of the time it should be pretty obvious when you try to solve it. You get kind of an infinity solution. And so in those cases, you can just say that it's under constrained. Yeah. Okay. But yeah, so that's it for trusses. And so when we come back on Tuesday, we'll start beam stuff. All right. And that'll be kind of a new class of problems that we haven't seen just yet. All right. So thank you guys for coming this week. I hope you guys have a good rest of your weekend, and I will see you guys on Tuesday. Thanks, everybody. Yeah, there's a emergency drill.
I know, but it's like lots.
Yeah, I know. We were all locked out. I had to be like, let us in. And then someone finally came in and unlocked the door.